Okay, hi everyone. My name is Karlee, for those who haven't met me yet. I work for the Canadian Forest Service, CFS, which is part of Natural Resources Canada. And first, I just want to say thank you to the organizers for having me here. It's pretty incredible to have a conference on an island like this, so I feel very lucky to be able to come. And today I'll be talking about subseasonal forecasting of fire weather using LSTMs or long short-term memory networks. So first, I've got a lot of questions this week about where I'm from. So I thought I'd just add a little map here of Canada. So the Northern Forestry Centre is located in Alberta, which the city is called Edmonton. In Cree, that is called here, which is, I say it wrong almost every time, but it's Amiskwaci Waskagan. And it's very important to us Canadians to recognize the Indigenous peoples on whose land we work. So that's how you spell it. And Edmonton is known for its rich natural resources. So we have a lot of oil and gas, a lot of logging, and also lots of cute beavers, lots of bison, and yeah, a lot of really rich Indigenous culture. So this is what Edmonton looks like. This is what they'll show you in like National Geographic to try to get you to come to Edmonton. That's like the nice angle. But really it looks like this, probably six or so months of the year. So, but yeah, so the overview of the presentation I'll be giving today. So first I'll start with an introduction to wildfires in Canada. I'll give a very quick summary of the FWI system. I know there's lots of experts in the room who know a lot more about it than I do, so I'm gonna try to go as fast as I can past that. And then I'll give a high-level overview of LSTMs, which Jonathan presented earlier today. And then the data pre-processing steps that we used, the model architecture, the results, and then I will finish with a 2023 case study. So wildfire is a very natural part of Canada's ecosystem. On average, we have about 8,000 fires a year, with about 2.4 million hectares burned on average. That is the average from the recorded historical data. Over the past about 10 years or so, it's gone up to about 4.2 million hectares per year. So we have a very large year-to-year variability in area burned. And about 3% of the largest fires are responsible for 97% of the total area burned. So some very, very large fires. 50% of the fires in Canada are lightning caused, but those fires lead to over 90% of the area burned. And in Canada, we have a lot of boreal forests, and boreal forests are known for having very high intensity crown fires, which are almost impossible or are impossible to put out once they reach that top crown fire. So this is a map of the population density of Canada. So I thought it was interesting to show that most of us live near the border, kind of in this triangle shape here, and then a lot in the east as well. And all of our fires are kind of up in the, or not all, sorry, let me rephrase that. Most of our large fires are up in the boreal forests, away from the main population areas of Canada. Right, this doesn't work. So this is an image of this year. So this is Manitoba. We had some really, really intense large wildfires in Manitoba with lots and lots of smoke plumes, which definitely hit the news, especially in the United States. And this is a picture of a fire from Flin Flon this year, which was one of the largest fires that we had. And another photo, again, from Manitoba from this year of one of the very large boreal forest fires that we had. So Canada has very high quality fire data going back all the way to 1959. Majority of that is in two data sets. So the National Fire Database, or NFDB, which actually isn't going to be maintained pretty much after this year. We're just going to be using NBAC, which is the National Burned Area Composite. So nationally, area burned is increasing, as is the number of fires, of large fires. And we have an increasing number of lightning-caused fires and overall a decreasing number of human-caused fires. We think that the drivers of that area burned increasing are rapid drying, early snowmelt, sustained drought, and extreme spring fire weather, obviously all related to climate change. So this is a map of the area burned in Canada over from 1959 to 2023. And you can see this really crazy 2023 year, which had about 15 million hectares burned, which was record-breaking in a lot of ways. And 2025 is probably sitting at about here. So we're at number 2 in 2025 for the number of area burned. This is the same plot, just shown in a different way. So this is cumulative area burned in Canada, but this is based off of satellite hotspots. So it's a little bit less accurate than the NBAC system. So this is the 2023 fire year. So you can see very, very crazy record-breaking year. And this is 2025 right here. So we are at number 2. So the FWI system is very much used in Canada by operational managers as well as researchers. So FWI is used as a general index of fire danger throughout the forested areas of Canada. And forecasted values are based on weather data. So we can also give FWI values per day. So today, if you were to go onto the Natural Resources Canada website, there would be a map on there of the FWI from today. But to forecast FWI values, we typically use numerical weather prediction models. So those numerical weather prediction models have skill up to about 7 days, or if you're using an ensemble, up to about 2 weeks. So this FWI system is used by wildland fire management agencies to guide decisions on fire danger and to provide information for public communication. So this is an example from the 2023 fire season on the one of the most high intensity days. So this is the fire weather index rating system numerically, and you can see we have a lot of red happening here over Alberta and Saskatchewan. Below is the fire M3 hotspots. So you can see that a lot of fire did happen in those really high predicted areas for FWI. This is also the satellite imagery from that same day. So you can see those hotspots, and again, a very, very large smoke plume. So I don't know if you guys saw it in the news, but the Americans were very angry at us for ruining their recreational activities from this smoke plume. So Canadians think that's pretty funny. Sorry, Jonathan. So if you're in Canada and you're kind of going near national parks, you'll see a lot of signs like this. So these signs are informed by the FWI system to try to communicate to the general public about which level of fire danger that they're at. So this is my favorite graphic that I've ever found on the FWI system. So instead of the traditional flow chart, it really helps to show which layers of soil we're talking about for the different moisture codes. So for the FWI system, the inputs are wind speed, relative humidity, rain, or precipitation, and temperature. And those inputs go into creating the fuel moisture codes, which are the FFMC, the DMC, and the DC. So those all represent different layers of depth that we're looking at here. And those go into making the fire behavior indices, which are the ISI, the initial spread index, the BUI, the buildup index, and the FWI. So in this project, we decided to forecast the BUI rather than the FWI. And we did that for a few different reasons. So BUI is most of the time associated with higher long-term predictability than the FWI. You can see here that it doesn't use wind as an input. So we're hoping that that means that we'll be able to predict it a little bit farther out than if we had chosen FWI. Aside from that, this was our first attempt at kind of trying to forecast any sort of the FWI indices using machine learning. So we often get questions about, okay, well, if that's the case, why not drought code or why not depth moisture code? And so we could is the answer to that. BUI is also used by fire management agencies, specifically in British Columbia, to tell people if there's a fire ban. So once it hits a certain number, BUI is used to put a stop to recreational fires. So the goal of this project is to forecast BUI. So like I said before, at the moment, FWI forecasts are used from numerical weather predictions, which have skill up to about 2 weeks if you're using an ensemble. So we were trying to forecast into the subseasonal range, so from 2 weeks up to several months, and seeing if we could get any performance from that. So We were using data-driven machine learning approaches, as there's been tons and tons of research going into obviously how that is a promising alternative from these more empirical formulas. So additionally, on top of trying to hit that subseasonal timescale, we were thinking, okay, how can we do that rather than just throwing BUI into the LSTM? So we also included teleconnections, which are large-scale climate drivers, to try to better predict that subseasonal seasonal predictability. So this is just a slide of showing all of the different machine learning applications, not all of them, some of them that have come out recently in this field. So what the point of this study is not to try the newest and best machine learning applications that have come out. It's more to see if we can use a really simple LSTM that runs really quickly, that could potentially be used operationally. So we decided to use an LSTM. There are a lot of publications using LSTMs. This one is an example using an LSTM for wildfire scale prediction, flood forecasting. There are a lot of different applications of this model. So I am going to probably skip a lot of this because Jonathan has gone over it earlier today, but this is the background of the LSTM. So it's a type of recurrent neural network, and LSTMs specifically are really good at long-term temporal dependencies within data. So traditional recurrent networks had a hard time kind of remembering information over long temporal sequences that you would pass in. And LSTMs have this special state here called a cell state, which has a memory in it. So when you pass a very long sequence, it does a good job at remembering the important information within that temporal sequence. So I'll probably just skip the rest of that. So our data pre-processing to use the LSTM model to predict BUI. So we calculated daily BUI using ERA5 data. And that was calculated using temperature, dew point temperature, precipitation, and wind. We then aggregated those daily BUI values into each hexel. So this is the plot of the hexels that we used for our model. So in total, there are about 17, but we dropped hexel 15 and 1 because those are areas of very low fire activity, so it wouldn't perform very well. So once we had a daily BUI value in each hexel, we then created weekly BUI values by taking the mean over 7 days. And then we obtained monthly teleconnections from NOAA, and those were also interpolated to weekly values. This is a table of all of the different teleconnections that we included in our model. So all the way from the Arctic oscillation to sea ice extent. So we tried to use basically everything that we could find, just throw it in there and see what happens. So this is an example of an actual input data sheet. So I found in a lot of machine learning talks, you're like, oh, we did this, and then threw it into the model, but it's like, how did you actually do that? So this is what our actual data looks like, and we're happy to provide this to anybody that wants to use it. So this is for a single hexel. So this is for hexel 9. So we have the BUI value, the year, week, the climatology, the anomaly, which is defined as the difference between the actual value and the climatology, and then all of these teleconnection values. So each hexel will have the same kind of input sheet. Not noted here is that we also used the encoding of week to represent the cyclical nature of it. So here it looks like we're including 1, 2, 3, 4, but we're not. We used the sine and cosine. So once we had a data sheet that looked like that, how do you actually put it into an LSTM? So you need to create input sequences from that input data. So to do testing of which teleconnections actually mattered to get better results, we created 2 different definitions of covariates. So we have fixed covariates and flexible covariates. So the fixed covariates are used in every single model run. The flexible covariates are allowed to use in individual model runs, but not all model runs. I'll promise this will make sense in a second. So the fixed covariates were the BUI anomaly, and the encoded week, and the flexible covariates were the teleconnections and the year. So that hexel plot that I showed before, each hexel we ran 512 models. So that's every possible combination of those fixed covariates and flexible covariates. So for a total of 7,680 models for all hexels. We then automatically pick the best combination of those covariates by selecting the lowest mean absolute error. So whichever model resulted in the lowest error per hexel, that's the one that we're going to use. So our LSTM, we tested a lot of different sequence lengths, but those were the best performing was a 12-week input. So we're passing 12 weeks of teleconnections and 12 weeks of BUI into the model and getting 5 weeks of BUI predicted. So this is a direct prediction LSTM, meaning that it predicts all 5 weeks of BUI at once, and then we use those values to compare against the actual BUI. For our data sets, we used data from 1979 to 2023, and this is an example of the split that we used. So we used temporal split like a lot of other people have shown today, where we have training data kind of chops off here, testing and then validation, or validation then testing. We normalized this using the robust scalar. We tried a lot of different scalar values and found that the robust scalar had the best performance in terms of MAE. And then this is a plot figure that I made trying to explain the input sequences for LSTMs. They can often be a very large source of confusion that people think you're actually just getting one number from each sequence, but in our case, we're getting 5. So we have 12 weeks of input data across the number of features that we've included. And for each sequence that we put in, we get 5 output BUI values. So this is our model architecture. So we implemented this in Python using Keras, which is TensorFlow. We tested a lot of different architectures, trying to remain with the goal that we're trying to use the simplest possible model to see if we could get good performance. So we did hyperparameter tuning using grid search CV with a time series split cross-validation. So it's very important when you're using temporal data that you're not using a random split because you can get data leakage and get inflated performance metrics. So these were the parameters that resulted in the lowest mean absolute error, and we also used early stopping. So this is the actual code of our model in Keras. So you can see we have one LSTM layer, a dropout layer, a dense layer with L2 regularization, another dense layer, and we used Atom. Our loss was MAE, mean absolute error, and we also tracked mean squared error. So our results. So again, for each hexel, we had the covariate combination that had the lowest MAE was selected as the final model for that hexel. In terms of teleconnections, we found that models that used those flexible covariates had better performance across the board. So including the teleconnections as scalar values helped the mean absolute error. So going forward in this presentation, I'll only be discussing models that included teleconnections. I'm going to be focusing on hexel 9, which is located here in Canada, just for the time series plots discussion because it has the highest mean annual area burned across Canada, and it also shows typical results across all of our hexels. And then I'll show plots, again like this, for normalized mean absolute area results, as well as precision recall area under the curve results. So this is a plot of all of the teleconnections that were selected across Canada. So this is the best combination. So all of these also include those fixed covariates, so BUI, BUI anomaly, and the week, and then as well as these additional teleconnections. I also didn't say, but year was also tested as a flexible covariate. So some of the hexels did use year to get the lowest mean absolute error. So this is an example of our results for time in the time series representation. So we have week 1 on the top, week 5 on the bottom. The model is in red. The observed or true BUI value is in purple, and the climatology is in green. The dashed lines are actually data that's been visually stitched together. It's not actually what the time series looks like. There's not a sinusoidal pattern in BUI. There's lots of zeros happening here. So this is where BUI is 0 because of winter, basically. So for week 1, you can see our LSTM does a pretty good job at capturing some of the extremes. It's missing a little bit here and here, but overall it's doing a pretty good job. And as we increase up to week 5, we're starting to approach the climatological mean or regress towards the mean. So this is another representation of normalized mean absolute error across all of our hexels for the best performing model. So for week 1, our model is beating climatology. This is against climatology. So blue means that the model outperformed climatology, and red means that the climatology had a lower mean absolute error than the model. So we used normalized mean absolute error instead of mean absolute error because across Canada we have a very, very wide range of BUI values. So on the West Coast, we typically have higher BUI values than on the East Coast. So just using mean absolute error can actually skew what we're looking at. So normalizing it by the average BUI of each hexel makes it more comparable across the country. So we've kind of stated that up to week 3, our LSTM seems to have good model skill. And then past that, week 4 and week 5, you can see that it starts to struggle a little bit compared to climatology. This is the same plot, but against persistence. So persistence is just showing that, okay, what if we just took the week 0 value and used that? So instead of comparing to climatology, we're now comparing to the week 0 value used across the board. So really the only important week here is week 1. Past that, it doesn't really matter. So you can see against persistence, our model does very well in the east and then not so well in the west. So additionally, on top of doing continuous performance, we also wanted to see if we could use this to get categorical performance for elevated fire weather. So in terms of operational side of things, saying this is the time series we got is not going to be very informative. And whereas we could say like, this is going to be a region of elevated fire weather, go there, look at this area. So to do that, we've here defined elevated fire weather as anything above the 75th percentile threshold. So for example, for hexel 9, the BUI, the 75th percentile threshold is 16. And so to create confusion matrices or to get precision and recall values, we've then said, okay, if the predicted BUI is 18, that's above the 75th percentile threshold, and so the classification for elevated fire weather is 1, or yes. So this is an example of those results for hexel 9. This on its own is kind of an internal thing. What we actually want to show people is the PRAUC, or the precision recall area under the curve, which is calculated in a very similar way, except that it calculates the BUI at every possible score threshold. So this is what you'll typically see where you have recall and precision. In lots of papers, they're going to show you an interpolated curve, so it looks very jagged here, but normally people will show you a smoothed out version of this curve. So this is the PRAUC results across all weeks across Canada. So again, using the 75th percentile threshold to say, is it elevated fire weather? How does our model perform? So again, best kind of at week 1. Week 2, week 3 are similar, and then again, it starts to not perform as well for weeks 4 and 5. And I guess too, when I look at this, the range is from 0.7 essentially to 100. So noting that for PRAUC, a complete random model would probably predict around 0.5. So as long as we're doing better than random, that's good. So as a summary of the model performance, models with teleconnections consistently outperformed the base model, or ones not using teleconnections, against climatology baselines. The best model performance is about 3-week lead times, and the performance gradually regresses towards the climatological mean. So now looking at that 2023 fire year. So this is one of the papers that my supervisor put out about the drivers and impacts of the 2023 wildfire season. And like I said, we had 15 million hectares burned, which was record-breaking across Canada. This is the area burned plot, again, of Canada. You can see 2023 here. So starting in April, we started to have evacuations in Canada. Again, another evacuation in May, another one. and then just basically evacuations up to September 6th. This is the plot of the area burned in Canada in 2023. So again, very large fires happening up here and also in Quebec. So what are the impacts of that? So fire management had very severe resource constraints. So we had Canada at 133 days continuously at the highest national preparedness level. So that basically means we're in an emergency, we need help. So 133 days in 2023, we're at that level. 5,500 firefighters were deployed from other countries. And there was about 200,000 evacuees and over 200 evacuations. And notably, the entire city of Yellowknife was evacuated. There was very poor air quality throughout Canada as well as in the United States. And this is an example of one of the news articles from the United States saying that there was really, really bad wildfire smoke. So how does our model perform in 2023? So we decided to look at two different hexels for this. So hexel 14 is right here in Canada, and hexel 10 is here. So one on the west and one on the east. So hexel 14, we see a little bit better performance here with the peaks, again, kind of missing this extreme peak here, and again, regressing towards the climatological mean. And then in hexel 10, we see worse results. So it's not doing a very good job at all getting that peak. So we were trying to understand why. What are we missing here? How come we're not getting this really good matching performance even at week 1? So hexel 14, we had very consistent environmental conditions, so very persistent drought. It was very much easier to predict than hexel 10, which we think was changing very rapidly. So using BUI, predicting BUI was not as straightforward. So summary, we've shown that machine learning can be a valuable tool for predicting fire weather up to about 3 weeks, so just slightly past what we're getting with numerical weather predictions. The architecture does not have to be complex to show some skill, especially for the weeks 1 to 3. That's when we need to start calling firefighters to come help in Canada. So that 3-week time frame is really useful for planning and resource mitigation. So future work, there's a lot of future work already happening on this project. This is actually quite old research that myself, Jessica Zerb, and P.S. Jane from the CFS were working on. So we do want to start to look at the more complicated architectures, complex architectures, autoencoders, even just adding an attention layer into the LSTM could be very beneficial. And using a hybrid model. So we've started to look at, can we use the FWI system and machine learning kind of together to get better results. So this is kind of our first attempt at trying to predict BUI using machine learning. So yeah, thank you for listening. And so just me and my supervisor are always very, very happy to collaborate with whoever wants to. So our emails are here. This is my supervisor, Piyush. He is a research scientist at the CFS. He's been with the CFS for 7 years. He's a great guy, and these are some of his publications that he's put out. So fire regime changes in Canada is a really hot topic right now. Also using comparative analysis of ensemble and deterministic methods for FWI system forecasting. And again, trying to figure out what the drivers of that 2023 wildfire season were. So we're very interested. Whoever wants to work with us, please just send us an email. But that's it. Thank you.